welcome to the second lesson of the 8th module, which is on combined stresses part 2. In fact, in the last lesson we have discussed about or we have introduced the concept of the combined stresses in a member, wherein a particular member is subjected to a combination of loads, say for example, axial load and the torsion, or the torsion and the bending, or could be axial load and bending, and various combinations of these individual loads. Now, we have also looked into that how do you compute the stresses when a particular member is subjected to the combinations of these different loads. Now, in this particular lesson we are going to look into some more aspects of such combined loads and how do we analyze them, and thereby we compute the values of the stresses. Hence, it is expected that once this particular lesson is completed, one should be able to be acquainted with some more aspects of combined loadings in a particular member, and thereby the evaluation of the combined stresses in members, and one should be in a position to evaluate stresses in structural members due to such a combination of loadings or combined loadings. The scope of this particular lesson therefore includes the recapitulation of previous lesson. Now, we will be looking into some aspects of the previous lesson which we have already discussed, and that we will be doing through the question answer session. Also, in this particular lesson we will be using the already developed formulae for evaluation of stresses for the combined actions of loadings. Now, as I have told you in the last lesson that in the previous modules we have developed some formulae for the individual load cases, like for example, we have looked into that how to evaluate stress in a member when that particular member is subjected to axial load, or if a particular member is subjected to a twisting moment or torsion, then how do we calculate the stresses because of the torsion in a member, or if the member is subjected to transverse loading for which there will be bending in the member, and thereby there will be bending stresses or shear stresses, and we have seen how to evaluate those stresses because of such bending moment and shear force. Now, here we are going to make use of those formulae which we have derived earlier in evaluating the stresses because of the combined loading. Also, we will be looking into some examples for evaluation of stresses in structural members which will be arising due to these combined loadings. Now, let us look into the answers of the questions which we had posed last time. The first question which was posed was, how will you evaluate the combined stresses if the member is subjected to an axial load and bending moment. That means, now that a particular member is subjected to not only the axial load, but also subjected to a bending moment. Now, in such situation how do you calculate the combined stresses? Now, we had looked into in the last lesson that there could be cases with reference to either a cantilever beam or simply supported beam, or for that matter any of such members where it is supported at suitable supports and is subjected to axial load as well as the transverse load. Now, when this particular member is subjected to, as in this case or in this case where you have the axial load and the transverse load, and here you have the moment as well. Now, if we like to calculate stress at any cross section in the member, then the stress will be because of this axial load, and this lateral load is going to cause a bending moment M and shear force V at this particular cross section, and there will be stresses because of this bending moment M and because of the shear force V. And finally, we will have to calculate the resulting stress because of all three actions. Now, as you know, we have seen that when a particular member is subjected to axial load, it is subjected to a stress which we call as normal stress, which is P by A, and since the load is compressive, so the stress also is compressive and which is uniform throughout the cross section. Now, because of the bending, there will be bending stress which we evaluate from m y by I, as we have seen earlier that sigma is equals to m y by I, where m is the bending moment, y is the distance at which you are computing the bending stress from the neutral axis, and I is the moment of inertia of the cross section of with respect to the neutral axis. Now, as we have seen that this bending stress with respect to the neutral axis, where the stress is 0, causes compression and tension in this particular case, and the top part above neutral axis is under compression and the bottom part below neutral axis is under tension. Now, bending also produces normal stress, as we have seen in the cross section. So, if we combine these two normal stresses together, the normal stress produced by the axial load and the normal stress produced by the bending, then we get a combined stress form either in this form or in this form or in this form, and we have discussed this why we get these three different situations. Now, apart from this bending stress and the normal stress, the transverse loading will cause a shear force as well, and because of shear force there will be shear stress in the member at that particular cross section. So, we got to compute the value of the shear stress at the point where we are computing the bending stress and the normal stress, and as you know the shear stress tau is equals to V q by I b, and this we have seen this particular formula how to calculate the value of the shear stress when we know the shear force at that particular cross section. So, we know the normal stress because of the axial load, we can compute the value of the normal stress because of the bending, and we can compute the value of the shear stress because of the shearing force which is acting. Now, the normal stresses because of the axial load and the bending can be combined together to give the resulting normal stress, and normal stress and shear stress, the two stresses which are acting in two different planes, we compute the values using either the transformation equations or using Mohr circle. Now, if you look into that in this particular figure, at these three locations, if we like to compute the value of the stresses, here we have the normal stress sigma, which is the P by A plus m y by I, or plus and minus depending on the magnitudes of these values, and tau is going to give you the shearing stress, which is V q by I b. So, we have the normal stress and we have the shearing stress, and these resulting stresses because of the normal stress and the shearing stresses can be computed from the Mohr circle. As you know that this is the sigma axis and this is the tau positive direction. Now, here if you plot the values of the normal stress and the shearing stress as we are computing from this formulae, and since you do not have any sigma y, so sigma y and tau, and if you join these two points together you get the circle, and thereby this gives you the maximum value of the normal stress, which we call as the sigma 1 or the principal stress. In fact, this is the answer for the second question as well. In fact, if you look into the question which we have for the second one, that how will you evaluate the principal stresses in if the member is subjected to axial load and bending moment. Now, as we have seen in the first one, that when you have the axial load and the bending moment, we can compute the values of the normal stress. Axial will give you the direct normal stress and bending will give you the normal stress in terms of compression and tension with respect to the neutral axis, and you can calculate the resulting normal stresses, and individually you can calculate the shear stress from the shear formula, which is B q by I b. Now, using this, if we like to calculate the resulting stress, which we call as the maximum value of the tensile or compressive stress, which is the principal stress maximum or minimum value, that we compute from the Mohr circle, and this is what has been done over here, that we can have this kind of relationship. That means, this is for the normal stress and this is for the shearing stress, and based on this normal stress and shear stress we can compute the value of the maximum principal stress sigma 1 or the minimum stress sigma 2, these are the principal stresses, and also we can compute the value of the in plane shear stresses, that what is the maximum value of the shearing stress that will be occurring at any point. Now, the third question which was posed was that what will be the value of the normal stress at the neutral axis, and probably I can answer this from this particular configuration itself or from this figure. Now, you see that we have an element chosen which is lying on the neutral axis. Now, as you know that when you compute the bending stress, the bending stress gives you a distribution, linear distribution with respect to the neutral axis. You get a compressive force or tensile and compressive depending on the kind of loading you have. Now, on the neutral axis, the value of the normal stress which is arising from bending is equals to 0. Now, if you have the combination of axial and the bending, then the normal stress which will be occurring at the neutral axis point or along the neutral axis is only for the axial stress, which is the normal stress sigma x equals to p by a, and there will not be any contribution from the bending along the neutral axis. However, if you choose the point above the neutral axis or below the neutral axis, there you will have the contribution from the bending, and thereby you will have the resulting normal stress. So, as you can see that all three questions which we had were related to the actions of the combined loading, where a member is subjected to the axial load and bending moment, and when axial load and bending moment occurs in a particular member simultaneously, we compute the resulting normal stress. Axial will give you the normal stress, bending also will give you the normal stress, and we can sum them together to get the resulting normal stress. And then because of the presence of the transverse load at that particular section, there will be shearing force as well, and shearing force will produce the shearing stress. So, you can have the resulting stress from the calculated value of the normal stress and the shearing stress using the Mohr circle. And now, you can visualize that when we had discussed in module 1 the transformation equation or the Mohr circle of stress, where because of the given stresses sigma and tau, we could evaluate that what will be the value of the principal stresses. Now, as you can see from the practical examples that a beam member is subjected to axial pull and the transverse load because of some loading situations, where we compute the normal stress and the shearing stress individually and then combine them together using the Mohr circle to find out the resulting maximum or minimum normal stresses and the maximum value of the shearing stresses. Well, this is what is shown over here, that if you get the stresses normal and the shearing stresses, then you can plot them in the Mohr circle. Here the normal stress is negative and the shearing stress is positive, and that is what you are getting corresponding to the first element. And when your normal stress is positive and the shearing stress also is positive, you get the point over here, and since sigma y is 0, we get the other point over here, we join them together. This is the center line of the Mohr circle, and the maximum value of the normal stress which is represented by this point in the circle gives you the maximum normal stress or the maximum tensile stress in the member, and this is the value of the sigma 2 or the minimum normal stress, and this is how we compute from the Mohr circle. Now, let us look into that if a member is subjected to an axial pull along with a twisting moment. Now, in the last lesson we had looked into some numerical examples where a member was subjected to the axial load and the transverse load which was causing bending in the member. Thereby, the member was under the action of axial load and the bending. Now, in this particular case we are going to consider that if a member is subjected to the axial load and a twisting moment, then what happens to the combined action of this loading. Now, if we are interested to find out the stress at this particular point, let us say this point is A, where we like to compute stresses because of the loading actions, like you have the axial pull P and there is a twisting moment which is positive in the sense that, as we have defined earlier, that when the vectorial direction points towards the positive x axis, we call that as a positive twisting moment, and at this end a positive twisting moment is acting in this member. Now, as we have seen earlier that because of this twisting moment, we get the shear stress at different point, which is given by T rho by G. Now, from the center if we go along the radius, this is rho. So, maximum shear stress will be occurring on the surface where R is maximum. Now, given the value of the twisting moment T, we can compute the value of the shear stress if we know the radius of this cross section, and J is the polar moment of inertia, which is I x plus I y, or in this particular case it will be I y plus I z, as we have called x as the longitudinal axis. Now, so we have the actions for the axial load as a normal stress, which is P by A, and twisting moment will give us the shear stress tau. So, if we look into this particular element, this element will be subjected to the shearing action. Now, because there is a twisting moment which is a positive twisting moment, on this element we will have the shear which will be acting in this form, and that is what is represented over here, which is resulted from this twisting moment T, and these are the complementary shear because of these shears, and sigma is the normal stress that is acting. Now, if this particular element is subjected to shear normal stress sigma and shearing stress tau, then the maximum normal stress we can compute again from the Mohr circle of stress. This is the sigma axis, this is the tau axis, and we can represent this particular plane where we have normal stress sigma and shear stress here is negative. So, this is sigma and shear is negative. So, on this side the point will be taken, and for the other side the normal stress is 0 and you have the shearing stress which is positive. So, the point will be here. Now, if you join these 2 points, the line which will cross the sigma axis at the point, that is the center of the circle. So, if we draw a circle with this radius, then we get the resulting Mohr circle, and this is the maximum value of the normal stress which we get from this particular circle, and this is the minimum value of this normal stress, this we call as sigma 2. So, this is sigma 1 and sigma 2, we can compute the value of the normal stresses. Also, this is the maximum and the minimum value of the shearing stresses, this is the positive tau, this is the negative tau, and this is the maximum shear stress that will be occurring at that particular point because of the action of axial pull and twisting moment. We will look into some examples how to compute this using numerical values. Now, let us look into that if a particular member is subjected to the again a combined loading action, but here the individual loadings are bending and twisting moment which are acting simultaneously in a member. So, we had seen the action of a twisting moment in a bar, that how do you calculate the shearing stress because of the twisting moment. Also, we have looked into that if a beam is subjected to the transverse loading, then how do you calculate the bending moment and the shear force, and consequently how do you compute the bending stress and the shearing stress. Now, if the member is subjected to the twisting moment as well as the bending, then what will be the consequence, or how do you calculate the stresses in such members. Now, if you look into this, that here we have a twisting moment which is acting, again it is a positive twisting moment, and a load P is acting at the end of this cantilever beam, this is fixed at this particular end. Now, this load which is acting at the free end of the cantilever beam will produce a moment at this section where we are interested to find out the stresses. We are interested to find out the stresses at point A and B on this particular cross section, let us say which is at a distance of A from the free end. Now, at this particular cross section the load P is going to cause a bending moment M which is equals to P into A, and also there will be a shear force which is equals to P. In fact, if we take a free body diagram, there we have P here, on this the moment will be in this direction and the shear force will be in this particular direction. Therefore, both moment and shear will be negative. Now, physically if you look into in this particular member, when this is loaded at the tip, the deflected form will be in this, and thereby the top surface will be under tension and the bottom will be under compression, and that we can verify from the numerical values as well or from the expressions as well. Now, you see M is minus P into A, and as you know that sigma is equals to minus M y by I. So, for M if we put minus P A into A, so this is plus P A y by I. So, thereby the stress is becoming positive, and positive indicates our tensile stress. So, from the expression also you get the same as you are looking here physically. Now, the question is that when this moment and the shear force is acting at this particular cross section, then what are the kinds of stresses we are going to get at point A and point B. Now, as you know that at point A because of the twisting moment there will be a shearing stress tau 1, which is equals to T into rho by j, where T is the twisting moment, rho is the value of the radius of the outer point, and j is the polar moment of inertia of the cross section. Also there will be shearing stress because of the shear force V, but the point A which is on the top surface, there as we have seen the shear stress because of the shear force is equals to 0. So, only contribution of the shear will be from the twisting moment at point A, and at point A because of this axial because of the bending, because the transverse load P is causing bending at A, which is equals to minus P into A, we will have a normal stress which is m y by I, this is sigma x. So, sigma x is equals to m y by I as it is indicated over here. So, at the top point we will have a normal stress sigma x, and there will be shearing stress tau 1, which is arising from the twisting moment only, and this is what is the representation of the stress pattern at that particular point A. Now, at point B, which is lying in the neutral axis, now as you have seen that at the neutral axis level the stress because of the bending is equals to 0. So, there will not be any contribution from the bending, thereby the value of the normal stress for that particular point will be 0. So, all we will have at that particular point is the shearing stress which is arising from the twisting moment and the shearing stress which is arising from the shear force value. So, tau 1 is arising from twisting moment, and tau 2 is equals to V q by I b depending on the amount of shear force you have at that particular section. We can compute the value of tau 2. So, if we combine these two together, tau 1 and tau 2, depending on the signs obviously that tau 1 and tau 2 I have shown in general as tau 1 plus tau 2, but depending on the signs it will have its value. So, you will get a resulting shearing stress at this particular section, and you will not have any normal stress. So, these are the two situations that we get corresponding to A and B, and if we plot these stresses in the Mohr cycle, then you get the situations in this form. Now, in the first case where you have the normal stress sigma x and tau 1, this is the point which is representing the stress, sigma y is 0 and you have the shearing stress only on that particular plane. So, if you join these 2 points, this particular point gives you the center of the Mohr cycle. So, this as a point and this as a center and this as the radius. If you plot the circle, you get the corresponding Mohr cycle of stress, and the maximum value of the sigma on this particular circle is this, which we call as sigma 1 the maximum normal stress, and this particular point is going to give us the minimum normal stress, and the maximum value of the shearing stress at that particular point will be equals to the radius, which is this is tau max. And corresponding to the other one where we do not have normal stress, but we have the resulting stress only tau 1 plus tau 2. So, you see we do not have any normal stress, but on this normal stress is 0, you have only the values of the taus, and if we, so this is the center of the circle, and if we plot the Mohr cycle, we get the normal stress as this, which is equals to the value of the tau 1 plus tau 2, and the minimum normal stress also is equals to tau 1 plus tau 2, which we have seen is the case of the pure shear. That means, at that particular point the state of pure shear is prevailing, and corresponding to that as we have seen in the past that how to compute the value of the normal stresses, we get the normal stress as equals to the shearing stress. Well, let us look into the examples. Now, this is the example which I had given to you last time, wherein there is a cantilever beam which is subjected to an axial pull or an axial load which is inclined at an angle of let us say theta. The magnitude of this load is 50 kilonewton, and this load is acting at an inclination of theta with respect to this axis of the beam. The cross section of the beam is a rectangular one having width 20 millimeter and the depth 120 millimeter. Now, we will have to compute the value, the maximum value of the maximum in plane shear stress and of course, the principal stresses. So, you got to compute the principal stresses and the maximum in plane shear stresses at point A of the beam. Now, point A, as you can see, is 20 millimeter away from the neutral axis of the beam, and the point is at a distance of 250 millimeter from the edge of the cantilever beam. So, we will have to compute the value of the principal stresses here and the value of the in plane shear stress. Now, this particular load, which is acting at an inclination with reference to the beam axis, which is at an angle of theta, can be decomposed into two directions. One is in the axial direction, another one is in the perpendicular direction, and thereby this axial direction force will cause an axial pull, or thereby there will be normal stress because of that, and the transverse loading, which is the component in the vertical direction, will cause a bending and a shear at this particular cross section. So, first we will have to find out that what are the magnitudes of the bending moment and what are the magnitude of the shearing force that is acting at this particular section, so that we can compute the value of the principal stress and the in plane shear stress. Now, this is what is indicated over here. First thing is that we have decomposed this inclined load, which is at an angle of theta, in two directions, one in the axial direction, one in the perpendicular to this axis direction. Now, since this is given as 3, 4 and 3, so the hypotenuse is 5. So, thereby cos theta is equals to 4 by 5, which is 0.8, and sin theta is equals to 3 by 5 is equals to 0.6. So, this value is 50 cos theta being 0.8. So, this is 40 kilonewton, and the vertical component is 50 sin theta, which is 0.6 is equals to 30 kilonewton. So, we have an axial force which is of magnitude 40 kilonewton, and we have a transverse load which is 30 kilonewton, which is acting at the tip of the beam. Now, what we are interested in is to evaluate the stress at point A, which is located as 20 millimeter from the axis of the beam and 250 millimeter from the edge of the beam, from the free end of the beam. Now, as we have seen, the axial load 40 kilonewton will cause a normal stress at this particular cross section, which is equals to P by A. So, P is 40 kilonewton converted into Newton divided by the cross sectional area, which is 20 times 120 millimeter square, and thereby we get a stress of 16.7 megapascal. Now, the point A will be subjected to a bending moment, and the magnitude of the bending moment will be equals to the load times this distance 250. Now, if we take the free body at this particular section, we have the load here, which is 30 kilonewton. We have the axial load, which is 40 kilonewton, and at this end you have the bending moment M and the shear force V. So, if you take the moment of the forces with respect to this, then we have moment plus 30 times 0.25 is equals to 0. So, bending moment we get as 7.5 kilonewton meter. This is of course negative, since they are acting in the same direction, and this will give, if we call this as V. So, V plus 30 is equals to 0, from the summation of vertical force is equals to 0, that gives V as equals to minus 30 kilonewton. So, we have a shear force of minus 30 kilonewton and bending moment of minus 7.5 kilonewton meter. Now, so because of this negative, this will become a positive stress, because sigma is equals to minus m y by I, and that will give us, and since y is positive, since it is above the neutral axis. So, we will have a stress, normal stress, which is tensile, which is arising because of the bending, and also we have the axial pull, which is a tensile force in nature. So, we have a tensile stress because of the axial pull. So, these two stresses, since they are of the same nature, because they are tensile, so we can add them together. So, normal stress because of the bending is equals to m y by I, and as we are seeing here, m is equals to 7.5 kilonewton meter into 10 to the power 6 will give you Newton millimeter. times y is 20 because point A is located at 20 millimeter away from the neutral axis, and I is equals to 2.88 into 10 to the power 6, which is B h cube by 12. So, once you substitute these values and the resulting value, if you calculate, it comes to 52 megapascal. So, 52 megapascal is the normal stress because of the bending, and 16.7 megapascal is the tensile stress because of the axial pull. So, the total stress that we have because of the bending and the normal stress is equals to 68.7 megapascal. So, this is the value of the normal stress sigma. Let us call this as say sigma x, that is being in the x direction. Now, in the y directions we do not have any normal stress. So, that is 0. Now, the shear force which we have seen that V is equals to minus 30 kilonewton will produce the shearing stress at this particular section A, which is equals to V q by I b, and V is 30 into 10 to the power 3. Now, q is the first moment of area of the cross section above the section where we are computing the stress. Now, we are computing the stress at this particular section, which is 20 millimeter away from the neutral axis. So, this section being 120, the half of it is 60. So, this particular part is 40. So, the area of this part is 40 times 20, and the distance of the CG of this particular section with respect to neutral axis is 40. So, we have 40 times 20 as the area, and 40 is the distance of the CG with respect to the neutral axis of the section above which we are computing the stress. So, this is Q and this is I and this is B, B is 20 millimeter. So, if we compute this, we get the shearing stress as 16.7 MPa, and since this is negative, it is acting in the negative direction of as we have taken our sign convention. So, this is the state of stress that we have at that particular point A, wherein we have the normal stress sigma x and the shearing stress tau. Now, as you know that at a particular point when we have the combination of the normal stress and the shearing stress, we can calculate the value of the maximum normal stresses and the maximum shear stresses using the transformation equations or using the Mosaic law. Now, if we plot these stresses in the Mosaic law, then we get the stress values in this form, that at this particular point where we have the negative shear stress and the positive sigma gives us this particular point. Positive sigma is of magnitude 68.7, that is the total normal stress, and this is the shearing stress 16.7 MPa, and on the other plane we have the shearing stress only, the normal stress is 0. So, if we join these 2 points wherever it cuts this sigma axis, this gives us the center of the Mohs circle. So, with this as center and if we take this as radius, we get the Mohs circle, and this is the point which represents the maximum value of the stress. Now, the value of the radius will be equals to the root of this distance, let us say this call as O, this point as A and this as A dashed. So, the radius O A dashed will be equals to root of O A square plus A dashed square. Now, O A is the distance which is from here to here, we know this stress is 68.7 and the center divides this into 2 equal half. So, 68.7 divided by 2 will give this particular distance, because this is sigma x minus sigma y by 2, this particular distance is sigma x minus sigma y by 2, and since sigma y is 0. So, this is sigma x by 2, which is 34.35 square, and this is 16.7 square. So, we get the radius value as 38.2 MPa. Now, when we like to compute the value of this particular stress sigma 1 will be equals to, if we call this as O dashed, sigma 1 will be equals to O dashed O plus the radius r, and O dashed O as you know is 68.7 divided by 2, which is 34.35. So, 34.35 plus 38.2 will give us the stress which is 72.55. This is the value of the maximum normal stress sigma 1, and consequently from this radius if we subtract this, we get the minimum value of the normal stress, which is 3.85, which is 38.2 minus 34.35, and the maximum value of the normal the shearing stress is the radius of this particular Mohr circle, and this radius is equals to 38.2 MPa. So, this is the value of the in plane shear stress. So, the maximum in plane shear stress that is occurring is 38.2 MPa. So, as you can see that this particular stress, normal stress being positive, that is tensile in nature. So, the maximum value of the tensile stress that you have is 72.55 MPa, which is the maximum principal stress. You have the maximum value of the compressive stress, which is 3.85 MPa, which is the minimum value of the principal stress, and then you have the resulting in plane stress, the maximum value of the in plane stress, shearing stress, which is 38.2 MPa, which is the radius of the Mohr circle. And so, once we know the individual stresses, we can compute the resulting stress using this Mohr circle. Now, let us look into the second example, which is the combination of the axial pull and the twisting moment. Now, this particular bar is subjected to an axial pull of 80 kilonewton, and also it is subjected to a twisting moment T, which is 1.1 kilonewton meter. So, this particular shaft, machine shaft of solid circular cross section of diameter 60 millimeter. So, this is a circular cross section, is a solid circular cross section, and the diameter of this particular shaft is 60 millimeter. Now, this is subjected to a tensile pull of 80 kilonewton and a twisting moment T is equals to 1.1 kilonewton meter. Now, you will have to evaluate the maximum tensile stress and in plane shear stress at point A. So, here this is the point A, where you have the where you will have to evaluate what will be the maximum value of the tensile stress and what will be the value of the in plane shear stress. Now, as we were discussing today about the stresses that will develop because of this axial pull and the twisting moment, as we have seen that axial pull is going to give us the normal stress, that P divided by the cross sectional area, the axial pull divided by the cross sectional area will give us the normal stress, and the twisting moment is going to produce the shearing stress. So, at the point A on the surface, you are going to have the normal stress and the shearing stress, and if you have the normal stress and shearing stress, you can compute the value of the maximum normal stress and the maximum shear stress from the Mohr circle, and let us look into that. Now, here you see that the normal stress which we are going to get because of the axial pull is equals to sigma, that is equals to P by A, and P is equals to 80 kilonewton. So, 80 times 10 to the power 3 is so much of Newton divided by area. Now, here since the diameter of the cross section is 60 millimeter and is a solid circular cross section. So, area is equals to pi by 4 times 60 square, and that gives us a value of 2827.43. So, the value of the normal stress sigma is equals to 28.3 megapascal, and the value of the shearing stress tau as it gets developed because of the twisting moment T is equals to T times rho by J, and in terms of the diameter, if we write tau as equals to T rho as d by 2 and J as pi d 4 divided by 32. As you know that polar moment of inertia for the circular section is pi d 4 by 32, and rho the maximum distance from the center, which is d by 2. Here we are going to get the maximum shearing stress. So, that is d by 2. So, eventually this gives us 16 T by pi d cube. Now, this is what has been used over here. So, 16 times T, T is 1.1 into 10 to the power 6 divided by pi times d cube, d is 60, that gives us a value of 26 megapascal. So, this is the value of the shearing stress and this is the value of the normal stress that is developed at point A because of the action of the axial tensile pull and because of the twisting moment. So, because of the actions of these two individual loading which are acting simultaneously, we are getting the stresses, the normal stress and the shearing stress of this much of magnitude, normal stress of 28.3 MPa and shearing stress of 26 MPa. Now, if we plot these stresses in the Mohr circle and the values or the directions are shown over here, sigma being the tensile stress is a positive, and tau here is giving shearing stress which is in the negative direction. Now, if we plot this particular stress distribution sigma and tau, that represents this particular point where sigma is equals to positive 28.3 and tau is negative 26 MPa, and on the other plane we do not have the normal stress, but the shearing stress is present which is also equals to 26 MPa, and if we join these 2 points together we get the center of the Mohr circle. So, taking this point as the center, let us call that as O, and O B as the radius, we draw the Mohr circle, and this particular point represents the value of the maximum normal stress which is represented by this particular distance, and which is equals to, as you know, this particular distance which we call as O dash, and O dash is equals to 28.3 by 2 because sigma y is 0 and this distance being sigma x minus sigma y by 2. So, we have 28.3 by 2 which is 14.15, and so this is also 14.15 and the shearing stress here is 26. So, the radius OB, this is OB, this is equals to 14.15 square plus 26 square, and we get a value of 29.6 megapascal. So, the value of this distance is equals to distance OO dash plus the radius, and OO dash is equals to 14.15 and 14.15 plus we have the radius which is equals to 29.6. So, if we add that, then we get the value which is 43.75, so much of megapascal. This we get for the maximum principal stress, and this being positive, this is the tensile stress that will be occurring in the member at that particular point, and this is the minimum principal stress which is equals to the radius 29.6 minus 14.15, and that gives us a value of 15.45 MPa. So, the maximum tensile stress that is occurring at that particular point is 43.75 MPa. The maximum compressive stress that is occurring is 15.45 MPa, and the maximum value of the shearing stress, the in plane shearing stress that is occurring, which is the radius of the Mohr circle, is equals to 29.6 megapascal. So, these are the values which we wanted to have. So, as you can see that because of the action of the axial pull of 80 kilonewton and a twisting moment of 1.1 kilonewton meter, the point A on the surface of this particular bar is subjected to a tensile stress which is equals to 43.75 megapascal and an in plane shear stress which is equals to 29.6 megapascal. So, these are the stresses that is acting on this particular member, and if you recollect that in the previous lesson we had shown you that this particular type of force distribution or the load combination comes in the case of a shaft which is used in the helicopter fan which moves, is subjected to a twisting moment, and because of this lift it is subjected to an axial pull as well. So, if we like to compute the value of the stresses, then we get the stress in this form in such shafts. Well, let us look into another interesting problem where this is a horizontal bracket A, B and C, it is in the horizontal plane. Now, this is subjected to a load at the tip. One is a vertical one which is of magnitude 2 kilonewton, and another one we have a load which is 3 kilonewton which is acting parallel to the arm AB. Now, what we need to do is that we need to compute the value of the stresses at a point D which is at the support, which is at A. Now, if we look into the cross section again is a solid circular one with a diameter of 60 millimeter, and we are interested to find out the stress at this particular point D. Now, what you will have to do is that you will have to compute the maximum tensile stress, maximum compressive stress and maximum in plane shear stress. You will have to compute these three quantities at point D for this particular member. Now, as you can visualize that these particular forces which are acting at the tip, if we transfer these forces at point B, they will be associated with some moments. Now, let us analyze the forces first, that how we transfer these forces to this tip of this particular beam. Now, this bracket ABC we can reduce it to a cantilever beam AB which is fixed at A and free at B, and in the process what we can do is we can shift this end loading to the point B, which is the tip of this cantilever part. Now, the vertical force which is of magnitude 2 kilonewton, if we shift at point B, then this is associated with a moment which is going to be a twisting moment. Now, so this vertical force 2 kilonewton is transferred at point B with a vertical force 2 kilonewton and a moment T, which is going to be a twisting moment for the bar AB. The horizontal force which is of magnitude 3 kilonewton, if we shift to this point B, this gives us an axial thrust to member AB and is associated with a moment which is a bending moment at point B of magnitude 3 kilonewton times this distance, which is equals to 0.4 meter. So, then this particular member AB, now if we disregard the member BC, part BC of the bracket, the member AB is subjected to a vertical load of magnitude 2 kilonewton, a horizontal load of magnitude or axial load of magnitude 3 kilonewton and a twisting moment T at the tip and a bending moment M at B. Now, the vertical load which is acting at the tip at point B of magnitude 2 kilonewton is also going to produce a bending moment at A. Now, if we look into the cross section, you will find that load P will cause a bending moment about the z axis. Now, already we have a moment M which is acting about y axis. We have a moment which is acting about y axis. Load P is going to cause a moment about z axis and we have T which is a twisting moment which is acting about the axis which is perpendicular to the board. Along with that, we have the axial thrust which is of magnitude 3 kilonewton. We have a axial compressive force which is equals to 3 kilonewton. Now, the interesting part is that we are interested to compute the value of the stress at point D. Now, if we look into this particular moment which is being produced by load P of 2 kilonewton. Now, this being the neutral axis, the stress on this because of this moment will be 0. So, at point D, the moment which is being produced by 2 kilonewton does not have any effect. So, this particular point will be subjected to a compressive stress because of the axial compressive force, will be subjected to a compressive stress because of the bending which is acting about y axis and will be subjected to the shearing action because of the twisting moment T that is acting at the end B. So, let us compute, and also now at the end A, because of this vertical load 2 kilonewton, there will be a shearing force component which will be producing the shearing stress. So, there will be shearing stress produced because of the twisting moment T, there will be shearing stress because of the shear force V, there will be bending stress because of M which is acting about about y axis, and there will be normal stress because of the axial compressive force. So, the normal stress sigma because of the axial compressive force is equals to the axial compressive force divided by the area, which is equals to 1.061 megapascal. Now, the bending stress is equals to m y by I. Now, the bending moment, as we have seen, that 3 kilonewton is the horizontal load times 0.4 millimeter 0.4 meter is the lever arm. So, 3 times 0.4 gives you 1.2 meter kilonewton meter as the bending moment. So, 1.2 into 10 to the power 6 into y is 30, because we are computing from the neutral axis at a distance which is equals to 30. So, m y and I is the moment of inertia which is equals to pi d4 by 64, which gives us this value. So, once we substitute that, we get the bending stress as 56.6 megapascal, which is compressive at this particular point. So, we have a normal stress which is compressive, we got a normal stress from the bending which is compressive. So, if we add these up, we get the total normal stress sigma which is equals to 57.661 megapascal. Now, we have the shearing stress tau which is arising from the twisting moment T, and twisting moment T is equals to 2 into 0.4 meter, which is equals to 0.8 kilonewton meter, and rho is the again is the distance which is 30, and J is twice the I. So, we get the stress as 18.86 megapascal. That is the shearing stress which is arising from the twisting moment. Also, the shearing force at this end is equals to this 2 kilonewton. So, for the 2 kilonewton, as we know that the shear stress distribution across the diameter of a circular cross section, as we have seen in the module of the shear stress, that the values is equals to 4/3 V by A. So, if we compute the value tau 2 equals to 4 V by 3 A, we get the magnitude of the shear stress as 0.94 megapascal. So, if we add these two tau 1 and tau 2, we get the resulting shearing stress that is acting at D is equals to 19.8 megapascal. So, you see this is the element which is at D, which is subjected to a normal compressive stress of this magnitude and a shearing stress of this magnitude. Now, if we plot these stresses in the Mohr circle, then we get the stresses like this, that we have at this point sigma which is negative and tau also is negative. So, this is the point which represents the plane where you have the normal stress and the shearing stress, and this is the plane perpendicular plane where we do not have any normal stress, but the shearing stress again is 19.8, and if we join these 2 points together, we get this as the center where it cuts the sigma axis, and considering this as the center and taking this O A as the radius, if we plot the circle, we get the Mohr circle of stress, and this is the stress which is the maximum compressive stress, and this is the stress which is going to give us the maximum tensile stress. Now, the value of the radius O A is equals to, as we have seen, is a half of this 57.66 and 19.8. If we take these two value, 57.66 divided by 2 will give you 28.83, that square, and vertical distance is 19.8 square. So, this is going to give us the value of the radius, which is equals to 35 megapascal. So, this is the value of the radius of this Mohr circle. Now, what we need to do is that we need to compute the value of the maximum compressive stress and the maximum tensile stress. Now, maximum compressive stress, as you can see from this particular diagram, this is equals to, let us call this as point B. So, OB is equals to the half the stress of 57.66 plus the radius. Now, let us call this point as O dash. So, OO dash is equals to 28.83, which is half of 57.66, and OB is equals to the radius, which is equals to 35. So, if we add these two, 28.83 plus 35, you get the stress which is the normal stress, and that is on the other side of the positive sigma axis. So, this is negative, and this we call as the compressive stress. So, this is the magnitude 63.83 megapascal is the compressive stress that is occurring at that particular point, and then the other side, the positive value of the Mohr cycle which we get, the normal stress which we get on this side, which is of positive magnitude, the 28.83 is this particular distance, and the radius is equals to 35, and if we add that, we get 6.17 megapascal, and this is the value of the maximum tensile stress. So, at the member at that particular point, you have the magnitude of the maximum compressive stress, which is 63.83 megapascal, and 6.17 is the 6.17 megapascal is the maximum tensile stress. Now, the value of the maximum shearing stress, in plane shearing stress, if you look into, will be given by the radius of this particular circle, which is given by this particular distance, and this is what is equals to the maximum value of the tau. That is on the tau axis, we get this is the point, this is the maximum value of the shearing stress, and tau max is equals to the radius, which is equals to 35 megapascal. So, we have these three quantities now, the maximum compressive stress as 63.83 megapascal, maximum tensile stress as 6.17 megapascal, and the maximum shearing stress as 35 megapascal. So, these are the values at that particular point when the bracket is subjected to tip loads, one in the vertical direction, another in the horizontal direction, which is parallel to AB. Now, these two forces compute the stresses at the support, which gives you the maximum tensile, maximum compressive and the shearing stresses of the magnitudes as we have calculated over here. Well, we have another example problem over here. Now, this is a sign board, as we have discussed last time, that many times we use these signs for giving the directions, and when the wind forces act on such signs, it produces combined force actions on the vertical members, and this particular board is subjected to wind load of 1.8 kilopascal. You will have to find out the maximum in plane shear stress at 3 point A, B and C. So, you solve this problem. I am going to discuss this in the next lesson. Well, then to summarize, in this particular lesson we have looked into the aspects of the previous lesson. Now, we have looked into some more aspects of the combined loading actions. In the last lesson we had discussed that what are the forms of different combined loadings that a member is subjected to. Now, in this particular case we have looked into some more aspects of such combined loading, and therefore, and thereby we have looked into some examples to evaluate combined stresses in member after analyzing the members for the proper loading. Now, these are the questions given for you. How will you evaluate the combined stresses in the member if the member is subjected to torsion and bending moment? How will you evaluate the principal stresses in the member if the member is subjected to torsion and bending moment? And what is the value of normal stress on the neutral axis when the member is subjected to torsion and bending? Well, we will discuss this in the next lesson. Meanwhile, you can go through the lesson and look into these questions. Thank you.